welcome to the Geomestic channel. In this video, we will take a look at an interesting relationship that segments have when intersecting in and around circles. To follow along with a guided notes worksheet, you can head down to the description and click on the link, print it off, and fill it out as we go. So in a circle, if you were to start drawing segments through any random point in or around the circle, so we start drawing segments through like so. You end up hitting the circle in 2 points through each of these segments. And in doing so, you create 2 little mini segments for each segment. So for example, in this segment right here going through the circle, I've got the distance from that point to the edge of the circle this way, I'll call that A, and then the distance from the point to the edge of the circle this way, call it B. And this happens throughout any segment that you draw through. So we'll call this C and D, and we'll say this is E and F. Okay, so there's a theorem that states that even though that all of these segments have different lengths, and thus all these little mini segments also have different lengths, the product of each pair of mini segments remains constant through any given point. In other words, if I take the product of A and B, so the 2 mini segments on this particular segment, so A times B, that's going to be equal to the product of any other pair of mini segments through this point. So that's going to be equal to the product of C times D, which is also equal to the product of E times F. And we can go on and on and on if we draw infinitely many segments through that point. Now, how do we prove this? Well, we prove it like we prove almost any other theorem. We use triangles. So let's take a look at why this is true. So we've got that same situation, any random point in the circle, segments going through that point. We'll say this is A and B, and point C, point D. And this little mini segment is A, this is B, that's C, that's D. Okay, so what we're going to do to prove this is we're going to create a couple of triangles. So we're going to draw the segment connecting C and A, draw the segment connecting B and D. And you can see we've got 2 triangles here. Now if you remember inscribed angles, which are angles that have a vertex on the edge of the circle, say for example angle A, which is this angle right here, is an inscribed angle that intercepts arc CB. Okay, we've also got angle D down here, which is this angle, and angle D also intercepts arc CB. And we know that inscribed angles that intercept the same arc are going to be congruent. Okay, so I've got that angle A, because it intercepts arc CB, and angle D, it intercepts arc CB. Those 2 inscribed angles are going to be congruent. Okay, so I know that angle A is congruent to angle D. And for the same reason, I can do the same thing on this side. I know that angle C, an inscribed angle C, which intercepts arc AD, and angle B, which also intercepts arc AB, I know that those 2 inscribed angles are going to be congruent as well. Okay, so I've got 2 pairs of inscribed angles. Angle C is also congruent to angle B. So in these 2 triangles, I've got 2 angles in this triangle that are congruent to 2 angles in this triangle. And by the angle-angle similarity postulate, I know that these 2 triangles must be similar to one another. Now, what does that mean? Similar triangles are the same shape, just different sizes. Or in other words, they have all congruent angles and their sides are proportional to one another. Okay? So because the sides are proportional, I know that I can set up proportions relating corresponding sides. So what I can say is that the ratio of A to D is equal to the ratio of C to B. Okay, so the sides in these 2 triangles are proportional, thus I can create this proportion. And in proportions, I can take cross products, meaning A times B, so cross, multiply, A times B is equal to the product here, C times D. Okay, and that's really the relationship that we want to get at with this situation. Okay, so going back to the original theorem, is that through any point in and around a circle, when I draw segments through there, those little mini segments, the products of those, A times B, so that's A times B here, is equal to the product of C times D. Okay, now this also holds true when the intersection point is not inside the circle, but outside the circle. So for example, say you have your circle here and you've got a point outside the circle. You've got a segment drawn to the circle, which again hits the circle in 2 points, just like as before. I've got another one, also hits the circle in 2 points. So we'll call this A, this is B, this is C and D. Now each segment, again, still hits the circle in 2 points, and the product of those distances is still constant. So the distance from the intersection point to the point where it intersects the edge of the circle here, times the distance from the intersection point to where it hits the circle here, is going to be constant regardless of where you draw that line through the circle. Now the formula looks a little bit different because I have these pieces that are outside the circle and the pieces inside the circle, but it's the same idea. So the distance from the point to the edge of the circle, which that distance in total is going to be A plus B, so that whole distance, times the distance from the intersection point to the circle the second time, so here, which is just A, is equal to any other instance, any other segment that happens. So this case here, we've got the whole distance, which is going to be C plus D, times the distance from the intersection point to the edge of the circle here, which is just C. Okay, so again, I'm still taking a product of two distances, setting them equal to each other. That distance product is constant. So I've got A plus B, the entire distance, times the piece on the outside of the circle, equals same thing on the other side. And again, this will all make a lot more sense when I start putting numbers in here, which we'll do with the examples at the end. Now to prove this, it's very similar to how we proved the first case. It's just creating sets of triangles with inscribed angles that you can conclude are congruent. You're going to get proportions like we did the last one, and it's going to be kind of the same idea. So this is the relationship that we're after in a case like this. Now the third case that this theorem encompasses is when one of the segments is a tangent segment. So it doesn't go through the circle, it just kind of hits the edge of the circle. So in this case it might look like this. You've got a segment hits the circle twice. In this case you got that secant segment, and then your other segment is a tangent segment where it hits the circle in just 1 point. Okay, so something like this. I'm going to call this segment T for tangent segment, and here we're just going to go with A and B again. So in this case, the top segment here, the theorem is going to look the same. You've got the length that goes all the way through the circle, which is going to be A plus B. So I've got here A plus B times the distance just to the edge of the circle here, which is A. Now in this case with the T, with the tangent segment, I don't really have two separate segments here. I've just got the one segment that hits the circle in 1 point. Okay, so what happens in the proof of this, which again is also with similar triangles. So if you did something like this, you're going to have a triangle here and then this triangle here. They're going to be similar. In the proof of this, what happens when you start setting up proportions of corresponding sides, this T value shows up twice in the proportion, and it happens to be in a place where you multiply those two together. So you end up with this T value being multiplied by itself, which is going to get you T times T, or T squared. Okay, so this is the relationship that we're going to have here. So we're just going to multiply that T value by itself. So this is how we get around a situation like this. Okay, so we have our three formulas, our three situations where either the lines or the segments cross inside of the circle, or if you have the segments that cross outside the circle, regardless if they're secant segments or tangent segments, that's what it's going to look like. Okay, so let's look at some examples, put some numbers in here, make a whole lot more sense. So we'll start with the two segments intersecting inside the circle. This is not going to be drawn any type of scale, so just bear with me here. Just go with the numbers that I draw. So let's say this is 6, this will be 10, call that 12, and x. Okay, so if we have the two segments intersecting inside the circle, the formula that we had was that the product of the two mini segments is constant, so they're equal to each other. So we'll call this A, B, C, and D. It doesn't really matter as long as A and B are on the same segment and C and D are on the same segment. So if we plug in what we have on segment number 1, we'll call it here 6 and x. I'll call those A and B, so it's 6 times x equals, and then C times D, 10 and 12. That's it, that's our setup right there. So 6 times x, which is just 6x, is equal to 10 times 12, which is 120. And we've got our equation, solve for x, divide both sides by 6. And we've got x equals 120 divided by 6 is 20. Okay, so you see in this situation, pretty simple setup, pretty simple solution, not a lot to it. You just have a little algebra problem to solve, you got your answer. Okay, let's look at one where the lines intersect outside the circle. So again, not drawn to scale, we'll go x inside. So we'll say this is our x, call that 7, call that 6, and call that 8. Okay, so when the lines again intersect outside the circle, looks like this to set it up, a plus b times a equals c plus d times c. Okay, so don't forget that these two pieces, the A and the C, these are the pieces that are outside of the circle. Okay, the portion of the segment that's outside the circle, make sure you get that. Okay, so A plus B, that is the distance from the intersection point all the way through to the edge of the circle on the other side. I'm adding those two pieces together. So if you call A 7 and B x, that will look like this. 7 plus x times A, which again, the piece or the segment on the outside of the circle, equals, same thing across the bottom, the entire distance here, we've got 6 plus 8 times the c value, the piece on the outside, which is 6. Okay, so you got a little bit more to clean up here, nothing too crazy. I've got 7 plus x times 7. What we're going to do here is we're going to distribute that 7. I'm going to multiply that to both terms on the inside, so I've got 7 times 7, which is 49. Plus 7 times x, which is just 7x. Here we're not going to go ahead and distribute, we're just going to go ahead and add those two together because those are two constant terms. 6 plus 8, that's 14. So I've got 14 and then times 6. So bring it down, 49 plus 7x equals 14 times 6 is 84. Isolate the variable here, so we've got 7x, we're going to subtract 49 from both sides. So we got 7x equals 84 minus 49, that is 35. And the last step, divide by 7. And we've got our x value, 35 divided by 7, that's 5. Okay, so a little bit more involved. Just be careful with your algebra, it should be fine. Okay, next case is with the tangent line. So we've got a tangent segment here, secant segment, hits it twice. Let's say x, 4, and 5. Alright, So our formula here, once again, if you have a tangent segment, just have to make sure to square it. So same idea on this secant piece. So you take a plus b times a, and the tangent piece you square it, t squared. Okay, call this a, call that b, call that t. So I've got 4 plus 5, the whole distance here, 4 plus 5, times a, 4, the piece on the outside, equals t squared in this case. That is my variable, that's x. So I've got x squared. 4 plus 5 is 9. 9 times 4 is 36. And then the last step here, because I've got that x squared, to get rid of that square, I'm going to take the square root of both sides, and I've got the square root of 36, which is 6. So we've got x equals 6. Okay, so I kept all these numbers real simple. Don't worry if you get a decimal value or if something doesn't seem like, it's working out exactly with these whole numbers. I just use these whole numbers to make it easier to kind of understand what's going on here. So if you get decimals, or if you have to square root something that's not a perfect square, no big deal. Let's do one more example. So let's do one where maybe it doesn't work out quite as nicely. We got to kind of figure through what we're doing on this last one here. So we're going to go back to the situation where you've got two secant segments intersecting on the outside. So we've got 4, 8, 10, and x. So in this situation, formula looks like this. Plug in what we have, start on the top, whole distance, 8 plus 4, times the piece on the outside, which is 8. Across the bottom, we've got x plus 10 times the piece on the outside, which is x. Okay, so we start to simplify here. 8 plus 4 is 12. In this case, we're going to distribute our x here, so you can already see why this is going to get a little hairy. We got x times x, which is x squared, and then x times 10, which is 10x. Okay, so we're going to be dealing with the quadratic in this case. 12 times 8, it's going to be 96. So we've got 96 equals x squared plus 10x. So now we got to kind of dig deep back into our algebra days here. We've got a quadratic equation that we've got to solve. Okay, we got to get rid of the x squared. You can't just square root both sides here because we have another x term. So we got to remember how to solve quadratics. To do so, we're going to get all the terms to one side of the equation. So we're going to subtract that 96, move that to the other side. And we're going to end up with something that looks like this. I'm going to move over here. So we've got 0, nothing left on the left side of the equation, equals x squared plus 10x minus 96. And if you remember how to solve quadratics, what we're going to do is we're going to kind of factor this thing out. We're going to look for terms two numbers that multiply together to get negative 96, that their sum is going to be positive 10. Okay, so again, you're looking for factors of negative 96, that their sum is positive 10. You can kind of go through and think about it, use a calculator, start dividing out. I know that the two factors that we're going to be looking at are 16 and negative 10. Or sorry, negative 6. My fault. Okay, 16 and negative 6. So if you multiply 16 times negative 6, you get negative 96. If you add 16 and negative 6, you get positive 10. So these are the two factors that I'm going to be using. And then to solve, what we're looking for is what values of x would make this whole expression here on this side 0. So if I plugged in a negative 16, that would make that whole thing 0. Or if I plugged in a positive 6, so 6 minus 6, that would make this 0 as well. So because it is a quadratic, I do have up to 2 solutions. But in this case, because we're looking at a length of a segment, one of these two solutions is an extraneous solution. It's not really going to make sense for what we're dealing with here in this problem. And you can tell that a negative segment length isn't going to make any sense. Okay, you can't have a negative 16 for a segment length. So in this case, that negative 16 is an extraneous solution, which means the value for x here is going to be 6. Okay, so there's a possibility in some circumstances where you are going to have to do a little bit more algebra. In this case, we've got that quadratic that we've got to solve. But other than that, pretty straightforward as long as you have your 3 formulas. Okay, so that's it for segments in circles or around circles. If this was helpful, please give this video a thumbs up and consider subscribing to the Geomestic channel if you would like to see more videos like this one. Thanks a lot for watching. We'll see you next time.